So, hello everyone. It's really nice to get invited to give a talk in this very interesting meeting, Neutrinos from Home. And I'm very thankful to the organizers for giving me this chance. So I was asked to share the status of the sterile neutrinos. And the title of my talk is The Curious Case of the Sterile Neutrino. As we will see that sterile neutrinos are really non-interacting entities, but still they are postulated to exist at all the scales, starting from the very high, the grand unified theory, to even at sub-eV scales. So to start with, about the neutrinos, uh, we know that neutrinos are neutral leptons and they come in three flavors, the nu E, nu mu, and nu tau. The three existence of three flavors are experimentally established. We also know that the flavor eigenstates are not the same as the mass eigenstate, and this leads to neutrino oscillations, which has also been observed. Now, the oscillation, apart from the mass, it also needs mixing between flavor eigenstates, and this is governed by the so-called PMNS mixing matrix. The oscillation experiments have measured the mass splittings and the mixing angles with considerable precision, most of them. And the limit on some of neutrino masses come from cosmology. As we know, oscillation experiment cannot measure the absolute mass. They measure the mass squared differences. So neutrino oscillation is a simple quantum mechanical phenomena. So if we start for simplicity with two neutrino flavors, say nu E and nu mu, then if neutrinos have mass, then this will be a superposition of mass eigenstates, and this is the mixing matrix, and this is governed by, for the case of two generation, by a mixing angle theta. As the neutrinos evolve in time, because they have different mass, they evolve differently, and that gives rise to a phase difference, and which ultimately gives rise to a probability, finite and non-zero probability of a nu E flavor going to a nu mu flavor after traveling through a distance L. Now, the amplitude of oscillation is governed by this sine square 2 theta, and the frequency is governed by this delta m square L by 4e term. So, what is important is that the delta m square to which a particular experiment is sensitive will depend on the L by E ratio, because the experiments are because for delta m square of the order of L by E, the oscillation effect is maximal. So what we see is that for oscillation, we need mass square difference, we need mixing angle, and that is what we need for neutrino oscillation. This is for two flavor, and it can be generalized to n flavors, and one gets a slightly complicated looking oscillation probability, and which now this U star means the CP phases also come, and but they depends inherently on the mass square differences and the mixing angle. So the mixing angles characterize this mixing matrix U, which for three flavors is called the UPMNS matrix. If we go to antineutrinos, then U is just replaced by U star, and one can calculate the antineutrino probabilities also. Now, we have evidence of neutrino oscillation from solar neutrinos, from atmospheric neutrinos, from reactor antineutrinos, and also from accelerator neutrinos. And together, all these experiments have established the three neutrino paradigm on a firm footing. And the three neutrino mixing oscillation is governed by three mixing angles, theta 2, 3, theta 1, 3, and theta 1, 2, and two mass square differences, two independent mass square differences, delta 3, 1 square and delta 2, 1 square. This is now well established, and most of the oscillation parameters are measured pretty well. Now the question is, are there more than three neutrinos? This is a very pertinent question, and Now, we know that if there is an extra sterile neutrino, then extra neutrino, then it has to be sterile, which implies that it should not have any standard model interaction, but it can mix with standard model neutrinos. The question is, if such a neutrino exists, what is its mass scale? Is it light? Is it heavy? And actually, sterile neutrinos appear at all possible mass scales. For instance, the experimentally there is some hint towards an EV scale sterile neutrino coming from the LSND and Mini-Boone experiments. And there are also some conjectures of sub-EV sterile neutrinos. Then the KV scale sterile neutrinos are candidates for dark matter. The MEV scale sterile neutrinos can be important for meson decay. One also studies GeV scale sterile neutrinos in the context of fixed target experiments, and then TeV scale sterile neutrinos for colliders. And also the sterile neutrinos occur at the grand unified in grand unified theories, and this gives rise to the seesaw model of neutrino mass generation, leptogenesis. And the TeV scale neutrinos are studied in the context of low scale seesaw, neutrinoless double beta decay, charged lepton flavor violation, etc. So this covers a vast energy scale and rich physics. By studying from the sterile neutrinos contribute to the physics at all energy scales. However, in this talk, I will mainly concentrate on the EV scale sterile neutrinos. So the first hint for an EV scale sterile neutrino came from the LSND experiment in the US. So the LSND experiment was measuring the nu mu bar, nu bar oscillations, and this nu mu bar were generated from meson decays, and these were about 50 MeV mean energy type of mesons, and they were covering a distance of 30 meter. So LSND experiment observe a 3.8 sigma excess over the standard model background. So this is what they observed, and this requires a delta m square if this is due to oscillation of nu mu bar going to nu e bar, then that requires a delta m square of the order of 0.2 electron volt square. Now we know, I told that there are two mass square differences like delta m square 2,1 or delta m square solar and delta m square 3,1 or delta m square atmospheric. Now from solar and atmospheric as well as accelerator and reactor data, we now know that delta m square solar is 10 to the minus 5 eV square and delta m square atmospheric is 10 to the minus 3 eV square. So this is the solar, mass range of delta m square and theta. This is the atmospheric mass range of delta m square, whereas LSND requires a slightly higher mass square difference. So which means that, with two scales of oscillation, one cannot simultaneously explain solar, atmospheric, and LSND. And this requires at least one additional sterile neutrino. So that is called the 3+1 mixture. Now we know that there are some constraints from Z decay to invisible particles from which one can say that the additional neutrino is sterile, that is, it has no standard model gauge interaction. So that's how LSND postulated a sterile neutrino, and the possible scenarios that were studied at that time, this was 1995, where 2 plus 2, where the where there is this is the atmospheric pair and this is the solar pair separated by the LSND gap, and the sterile neutrino can contribute either to the atmospheric anomaly or to the solar anomaly. However, the solar and atmospheric data subsequently disfavored this scenario. The other scenario which people studied after the LSND results came were the 3+1 scenario, in which a single sterile neutrino is added. So the solar and atmospheric neutrinos are the usual three flavor scenario. With that, the one high scale sterile neutrino is added at the LSND scale, and that can affect the solar and atmospheric oscillations, but not too much. So this was the 3+1 scheme. And when we consider the mixing, then there will be additional mixing angles, theta 1 4, theta 2 4, and theta 3 4, and then there are additional phases, delta 1 4 and delta 2 4, apart from the three generation masses, and apart from the 3 generation mixing and phases. And there is also a Majorana phase, extra Majorana phases, but for the oscillation experiments, we are not concerned with these. So the LSND results, there were, I will come to it little later, although LSND got a positive evidence for nu mu bar, nu e bar oscillations, there were other experiments like Carmen, and then there were reactor experiments like Puget. They have not observed such oscillations, so it was not very clear what is happening, and that's why the mini boon experiment was planned, and which would use the booster neutrino beam in Fermilab, and the L was 500 meter, and the energy was in the 200 MeV to 3 GeV range, and it can study nu mu nu e and nu mu bar nu e bar oscillations. Now this has a different L and E, but the L by E is same as LSND. And since the delta M square goes as L by E, so mini boon can study the same L by E, but because it is a different energy range, it has a different systematics. So Minibun Minibun ran from 2002 to 2017, and this is the final Minibun results published in 2008. And what they observed was a 4.8 sigma excess in electron-like events for both neutrinos and antineutrinos. So Minibun corroborated the LSND result. Not only this, Minibun found something else. So this dashed line is the oscillation fit, and this black are the data points. And what we see is that the oscillation does not fit well at low energies. There is some excess, and also at the forward angle. So this is cos theta 1. So there is some problem at low energy where the oscillation hypothesis cannot explain the mini-boon data, and that came to known as the mini-boon low energy excess. So if we compare LSND and mini-boon combined, then the combined significance for nu mu nu e oscillation, nu mu bar oscillation, and is 6 sigma. And this is the allowed region in the delta M square sine square 2 theta plane, assuming a 2 neutrino fit. So this shaded region is the LSND, this blue is the 90%, gray is the 99% confidence level region, and this orange region is the 4 sigma region of mini-boon. So so here the mini-boon neutrino and antineutrino is included. So the mini-boon and region is consistent with the LSND region. There are overlaps in the parameter space. Now, apart from mini-boon and LSND, there was some other experimental evidences which were favoring a EV scale sterile neutrino. So one came from the gallium source anomaly. So the gallium experiments, Galax and Sage observed the solar neutrinos, and they were trying to calibrate their experiment using a 51 chromium, which mimics the 0.8 MeV solar neutrino line. So that is where they were sensitive to, and so they were trying to get the the solar the calibration done. And what they found was that if they do the ratio of the N experiment to N theory, they find that there is about a 3 sigma deficit. Then the best experiment, which ran for 2011 to 2021, was planned to test these results. Now, the best experiment had 2 zones, and they had an inner zone and outer zone, and they could measure the PEE. And what they did was they confirmed the overall deficit at 4 sigma. So they supported the Sage and Galax result, and the combined result is like 0.80 plus minus 0.05. However, they did not observe any variation with distance. So this is the delta M square sine square 2 theta parameter space. And what one can see is that, this delta M, there is not much sensitivity in delta M square, because they did not really observe any variation with distance. All they observed is a deficit. So it was guided by the mixing angle, the deficit. And so the possibilities could be inaccuracies, other possibilities in cross section, source strength, counting efficiency, extraction efficiency, etc. And there is at present no clear answer to this. Another anomaly which came out was the reactor antineutrino anomaly. So the flux measurement of several reactors showed deficit compared to the theoretical calculation. So this is the result from various reactors, and this is the average, and it was about a 3 sigma effect, this deficit, and the main uncertainty was coming from the 235 uranium and 239 plutonium fluxes. However, there was a recalculation of reactor antineutrino flux, which predicted a lower 235 uranium flux. And with that, this reactor antineutrino anomaly was not very significant. And then it was clear that it is probably not a neutrino deficit issue. It is more of a flux calculation issue. Now, I talked a little bit about the disappearance and appearance tension. And here I am showing that. So the LSND and mini-Boone experiments were appearance experiments, which means that, if they start from a flavor alpha, they get a flavor beta. So they were starting from nu mu and they were getting nu e. So, or nu mu bar, nu e bar. However, there are experiments which can measure the deficit. So there were a lot of experiments, accelerator based experiments like CDHS, which was measuring a deficit in the muon neutrino flux. Then the MINOS and MINOS plus experiment also measured this disappearance. Then the reactor experiments measured the PEE, P nu E. So they measured the disappearance of the deficit in the electron neutrino flux. So this is called the disappearance channel, that as if some of the neutrinos are disappearing, so they are getting a deficit. So what happened is that, all these disappearance experiments never observed any signature of oscillation. And the PEE, which is measured by the reactor neutrinos, they depends on UE4 square. The P mu mu depends on U mu 4 square, and P mu E depends on U mu 4 square, U phi E 4 square. So all these get somewhat related. And here I show a summary result. This black is for all nu mu disappearance combined. And this red is the allowed region from the appearance channels. So what we can see is that the disappearance, the appearance results have a severe tension, and the combined disappearance results rule out the the allowed region from LSND mini-Boone experiments. Like this problem became more severe with MINOS and MINOS plus, and then this is also Ice Cube SK. They also measured the the atmospheric neutrino experiments can also measure this sterile neutrino content, and then they also found that this kind of a region from their disappearance channel. So this was the situation. Now, this kind of, there are also, as I said, reactor experiments, and many short baseline reactor experiments were planned for testing this. So for this, the L is about 6 to 24 meter. And they can study the reactor neutrino spectra. They can measure the near-far ratio to tackle flux uncertainty. For instance, there is the Korean project NEOS, and this yellow are the projects which gave data. Then there is stereo, then there is neutrino 4 in Russia, then also dance, and then prospect, which is in the US. And so all these experiments gave some results, and some of the recent results of this, for instance, from the neutrino 4 collaboration, which was very confusing, because they observed some oscillatory pattern with delta m square of 7 ev square, and this was close to 3 sigma. And this is a recent result from the prospect experiment. However, prospect did not observe any neutrino oscillations. So here I present the global picture from the reactor neutrinos. So, and also the gallium. So you can see that this shaded region is the region for the gallium anomaly or including the best. And this black is the neutrino 4 best fit around 7 eV square. And these lines are like the exclusion regions, and this black is the prospect exclusion region, and this green is the stereo exclusion region. This orange is the neos exclusion region. So we can see that, first of all, this neutrino 4 allowed region is excluded by uh, other experiments. Then there was this is the gallium anomaly allowed region. Some part of it was allowed at high delta M square, but the prospect result also rules out most of this part. So here also it is showing this Catherine result, which I mentioned earlier, that Catherine was ruling out this part high sine square 2 theta, but these reactor experiments can probe from smaller sine square 2 theta also. So then let us come to the low energy excess in mini-boon. I mentioned that mini-boon observed a low energy neutrinos over the background, and this green is the electron neutrinos, and this yellow is the NC background, which is the, produces photon in the final state. So now the question is whether sterile neutrinos can explain this. And what is found was that even if we have 3 plus n neutrino signal, they cannot explain the mini-boon low energy anomaly. So this is the low energy anomaly, and then this black is with 3 plus 3, but nothing could explain it. So then the question is, obvious question is whether it is due to the background effect. And Minibone can observe this kind of events. One is nu mu charge current, which is muon, then the electron and the pions, which can give to photons. Now, these photons can also give E plus E minus. And Minibund cannot distinguish between Cherenkov cone of electrons and those coming from single photons. So the single photons coming from the neutral current background, can they explain the excess? But we have seen here earlier that they cannot explain the excess. So the microboon experiment is a liquid argon time projection chamber experiment, which was planned to test this, and its primary goal was to see if the mini-boon low energy excess is due to the SM background or it is due to the electron neutrinos originating from the, the nu mu nu e oscillations. This has the same beam, but as my mini-boon, but they have similar baseline, but they have different technology. And the liquid argon detectors have excellent resolution, so they can separate between the electrons and photons. So microboon results came out in 21, and they disfavored the delta to gamma, the neutral current background, as the origin of the low energy excess. And they also did not find any electron neutrino excess in data. So these are the microboon observed. And if we have the electron excess, then we get this red prediction. So microboon is not showing the electron excess. However, some studies showed that the electron neutrino excess cannot be excluded in a model independent way. Several questions were raised at this point, that whether it is due to new physics. And what one is awaiting now is the result from all 3 detectors in the short baseline neutrino detector program of Fermilab. So I will come to that, but this is a summary of the 3 plus 1 feet of mini-boon and micro-boon. So what we can see is that, this red is the mini-boon feet, and then this is the combined feet. So what we see is that the quality of the feet worsens with micro-boon. If we add mini-boon to micro-boon, mini-boon only delta chi square was 27.8 per 3. So this is the no oscillation, how the no oscillation is ruled out. But combination is the delta chi square is slightly worsens, but the 3 plus 1 is not ruled out if we combine microboon and mini-boon. However, the appearance and disappearance tension is very difficult to resolve. Now, the short baseline program in Fermilab will have three detectors: short baseline neutrino detector, microboon, which has already given data, and Icarus. And what they will do is, they are situated at three different distances. So they will sample the beam at different distances. And this detector can also near detector, and it can also control the systematics. This is currently operational and taking data. They can measure appearance and disappearance channels, and it is expected that this experiment will finally have some solution for the sterile neutrino. They can say something to resolve these problems. Now, I talked about the 3+1 case, and when I talked about the 3+1 case, then I showed just one sterile neutrino above the three neutrinos at a EV square scale. However, the point is that this there can be, if we have a EV square neutrino, then there can be other options also why the EV square is not below. And also here, this is like I have assumed that normal hierarchy, and this is normal hierarchy and a sterile neutrino, and this is inverted hierarchy plus a sterile neutrino. So normal hierarchy means that the I have delta 2 1, and the third state is greater than the has a higher mass than the 2 and 1. And inverted ordering means the third eigenstate is below 2 and 1, but the sterile can be above this at EV square. Another possibility is sterile can be below. However, these scenarios are very strictly constrained also by cosmology, so one has to see that. So, we know that the radiation density in the early universe has a component of the photon density, plus this is the neutrino contribution in the standard scenario. And this N effective, this is the energy density of the relativistic neutrinos. And in the standard model, the N effective is 3.044 plus minus 0.002. However, if there are some other radiation, then this whole thing is combined effect of the neutrinos and the other radiation, and we can define a delta N effective, which is this N effective minus the N effective standard model. Now, N effective is measured from various processes like BBN, then large scale structures, cosmic microwave background, and there is a bound. This also depends little bit on the model, but this is a lambda CDM, standard lambda CDM model. Plus, with certain constraints, what one finds is N effective is 3.11, and the sum of the neutrino masses is 0.16 electron volt. Now, this is of course model dependent, but this is one of the models which I am considering for showing some results. Now, what happens when we have a sterile neutrino? Sterile neutrinos can contribute to N effective, as I have shown, and they can also contribute to the sum of the neutrino masses. And for massive neutrinos, we have two parameters. One is the N effective and one is the MS effective. And in this sigma, what we add is the three mass, the three sum of the three neutrino states plus one MS effective. Now, fully thermalized neutrinos, delta N effective will be 1. If we have the sterile neutrinos fully thermalized, then active and sterile states will be in equilibrium and delta N effective will be 1. But what we are seeing from the data is that, delta N effective is like if we take this value, then N effective minus N effective SM, it is less than 1. And so for that, one has to take a non-thermal and partially thermal distribution of the sterile neutrinos, in which case this MS effective will be delta N effective times the M4. If delta N effective is 1, then this MS effective is M4. Otherwise, we have to take the MS effective. So what we studied was whether the sum of neutrino masses in all the different spectrums is consistent with cosmology or not. And what we found was that the model in which we have normal ordering and the sterile neutrino is above this is only allowed. This is the green line, which is allowed from the 10 parameter model that we have considered. All others are ruled out. The scenarios when the sterile neutrinos are much below the sterile neutrino is lightest is ruled out very significantly. However, the scenario with IO is also sort of disfavored. So that's how SNO, NO, and 3 plus 1 is the minimal model. Like people have considered resolving the disappearance and appearance tension by adding going to 3 plus 2, but then it will also be very much problematic with this kind of standard cosmology. Now, this was about the EV scale sterile neutrino, and with the little time that I have left, I wanted to discuss about the KV scale sterile neutrino. So this pertains to the question that whether the neutrinos can be a candidate for dark matter or not. Since neutrinos are weakly interacting and they do not couple to the photons, it seemed that they can be an ideal candidate for the dark matter, but there is a very robust argument coming from the phase space which rules out the standard neutrinos as a candidate for dark matter. And this happens because neutrinos obey Pauli exclusion principle, so which forbids packing of too many of them in a gravitationally bound object. Now, most compact dark matter dominated object observed is the dwarf spheroidal galaxies. And to match the dark matter density of these, the neutrinos have to be tightly packed. And that gives a bound on the neutrino mass of the order of 200 electron volt. So this is the famous Tremen and Gun bound, which they gave much before, around 1979. And with the dwarf galaxy data, this bound is about 190 to 220 electron volt. Now the question is whether sterile neutrinos can be a candidate for dark matter. So in this we add a sterile neutrino which is mixed with the active neutrino, and the simplest production will be via this oscillation. So this is a simple two generation picture, and this is a famous Doddelson-Withdraw limit. Now, in this, the sterile neutrino initially do not have any distribution. They arise because of oscillation. So we start with a dilute and non-thermal distribution of sterile neutrinos, and the Tremen-Gun bound states that it has to be greater than 2 keV. Also, because they mix with the active neutrinos, they can have this kind of diagram where by a W exchange, they can emit a photon. And this is because these are KV sterile neutrinos, they can give rise to X-ray lines. And this rate is proportional to the mass of the sterile neutrino and the mixing angle. However, this sterile neutrino should not decay in the scale to be a valid dark matter candidate. They should be stable. So the lifetime has to be age greater than the age of the universe, which puts a bound on the mixing angle, and this mixing angle is quite small. So for the sterile neutrinos to be a dark matter candidate, their mass has to be greater than 2 keV, and the mixing angle has to be quite small. For instance, for 50 keV, the mixing angle will be of the order of 10 to the minus 7, has to be less than 10 to the minus 7. So the Doddelson-Withdraw mechanism says that initially the nu A is in thermal equilibrium via weak interactions, and nu A's population is negligible and out of equilibrium. However, as the universe expands, the nu A oscillates to nu A's, and also the nu A will collide, and these collisions sort of act as measurement, and this is like the quantum Zeno effect which suppress the conversion. So that is sort of a damping, that adds sort of a damping, and this overall process controls the the sterile neutrino population in the early universe. Now one can solve the distribution equation. It depends on the mass square difference. This delta is the m square by 2e. It depends on the mixing angle. This gamma is the total rate which comes in the denominator because of the damping effect. And because in the early universe we are in the matter, there are matter effects in the neutrino propagation that also has to be considered. When we consider the LSND and mini-boon, we considered vacuum oscillations in vacuum. However, for solar and atmospheric neutrinos also the matter effects are important, and the early universe also it is very important. However, and this is the kind of an MSW process. However, in the standard MSW, what happens is that this is the matter potential due to the electron density and the other, particle density. And if these two are equal, then there can be a resonance and the mixing angle can get enhanced in matter. However, in this case, the potential comes out with a positive sign. So there is no resonance in the Doddelson-Withdraw mechanism. So this is the standard Dodelson-Withdraw mechanism line to satisfy the relic density. For this to be the dark matter, they have to satisfy the relic density. However, what we see is that, this is also the bound from the X-ray, because as I said, this nu S can go to nu A gamma, and they emit a sharp X-ray line which is at Mn by 2, and this is not observed. So from that, this whole parameter space is ruled out, and the standard Dodelson withdraw falls in the disfavored parameter space. And here for the low mass region, there is some possibility was there, but that is ruled out by the Tremengun bound. So what we see is that standard Dodelson withdraw is very interesting. If a sterile neutrino has, it should happen, but it cannot be a viable candidate of dark matter satisfying the relic density constraints. So there are many way outs people have thought. One is the Shih-Fuller mechanism, where one introduces a resonance by assuming a presence of a large lepton asymmetry, but the origin of such an asymmetry is not very clear. Also, recently, some ideas have become very popular, which is a neutrino self-interaction mediated by singlet scalar. So there is active neutrino self-interaction. People consider sterile neutrino self-interaction. And recently, we have also studied active sterile non-standard interaction. So what happens is that there is a singlet scalar. It couples to two active neutrinos. We have these kind of terms in the Lagrangian. So this is a sterile self-interaction, and this is an active sterile self-interaction. All three processes can open up some parameter space and allow the KV scale sterile neutrino to be a dark matter. I will show one result from our paper, where what we have done is that in presence of an active sterile interaction, what we find is that there is a number changing reaction. So in the standard Dodelson withdraw or in the other active-active or sterile-sterile self-interaction processes, to produce the sterile neutrino initially, one needs the oscillation. However, in our case, we have a non-standard interaction where the active-active scattering can produce the sterile. So nu A can produce the nu S, and we don't need the oscillation. So we don't need the Dodelson withdraw. So Dodelson withdraw can also happen, but to start with, to build up the sterile population, we don't need. And that allows this wide parameter space and even very small values of mixing angle. In the other methods, other self-interactions, these kind of regions, very small mixing angle regions, cannot produce the enough relic abundance. However, in our case, because initially the sterile neutrino population is higher because of the scattering, our model can reach the relic density for this kind of values of the mediator mass and in this white region. So this is about the KV, and I also said that sterile neutrinos occur at Gatt scale, and neutrino oscillation experiments have shown neutrinos have mass, and cosmological bound on neutrino masses is, like I said, it varies from model to model, like so it is like 0.26. So neutrino masses are very small, and the mixing angles are also much smaller than the mixing angles are also different, and neutrino masses are much smaller than the other fermion masses. And what explains these small masses? And a natural way to explain this is the seesaw mechanism, which relates the smallness of neutrino masses with new physics at high scale. And this happens due to tree-level exchange of some heavy particle at the high scale, and that gives rise to an effective operator. And this is the seesaw mechanism. And the type 1 seesaw, the mediator is the sterile neutrino. So the type 1 seesaw needs very high scale sterile neutrino to give small neutrino masses. And this operator, Weinberg operator LLHH, violates lepton number, because L and LC have opposite, L and LC bar have same lepton number by 2 units. So this shows that neutrinos are Majorana, and this gives rise to neutrinoless double beta decay. Also, this heavy mediator or the sterile neutrinos can decay of these can give rise to leptogenesis. So sterile neutrinos have a lot of interesting physics even at the high scale. Although it's very difficult, these are like 10 to the 12 GeV, 14 GeV to have any observable signature. And with the collider physics, with the LHC, there were a lot of models that whether one can reduce this energy scale and have a low scale seesaw models, and this gives these are the TV scale seesaw models which have also been studied. So this brings me to the summary of my talk. The sterile neutrinos can exist at all energy scale. There are some hints in favor of EV scale sterile neutrinos coming from LSND, mini-boon, gallium source experiments. However, there is strong tension in disappearance and appearance experiments. EV scale sterile is a constraint from cosmology, and the KV scale sterile neutrino can be a viable dark matter candidate. However, the simple Dodelson-Withdraw oscillation-induced mechanism of producing sterile neutrino dark matter is disfavored by X-ray and relic density constraints. But self-interactions among neutrinos can open up allowed parameter space, and heavy sterile species can give rise to small neutrino masses by seesaw mechanism. So the thing is that, the situation is still very exciting, and some experiments are coming at least to solve this. We are looking forward for a solution to this LSND mini-boon anomalies. So this is the end that, so they are fundraising, and he's saying it's full of sterile neutrinos. So $10 for an empty bottle. He is asking that, why are you asking $10? And it is saying that it's full of sterile neutrinos. So I don't know if really we have a signature for sterile neutrino, whether it's a $10 or $1 million. Thank you.